Hello, in this video we're going to cover section 1.6 Applications of Functions in Business and Economics. We start our brief calculus class here because we want to look at situations where the answers to mathematical questions would really impact our understanding of a real-world situation. At Ball State, most of the students who take Math 132 are business majors, so we naturally have a business focus in these first couple of applications. So as we go through and just scan each of these objectives, definitely in a business setting you would be interested in total cost, revenue, and profit. Knowing information about marginal costs can tell you a lot about what's going on in that situation. And we can look at how some of the algebra skills we already have would allow us to do at least an introductory analysis of this business situation. So we'll be looking at finding break-even points, finding market equilibrium, at least for sections where the functions that we look at are not too complicated. Once we hit the next section, the functions will get a little bit more complicated, and then beyond that, we really have to have calculus tools to be able to analyze functions once they get more involved than quadratics, because at that point algebra just really isn't going to be able to handle, it doesn't have the tools that we need to analyze the functions like we want. Our first examples are going to deal with cost, revenue, and profit functions. So out of the business context, we observe that profit is equal to revenue minus costs, where P of x is equal to the profit from the sale of x units, R of x is the total revenue from the sale of x units, and C of x is the total cost of production and sale of x units. In some situations, these functions will be given to you in an example, but in other situations, you'll have to construct the revenue and the cost functions. When we think about the revenue function, revenue is equal to a price per unit times a number of units. When we think about the cost function, cost typically has variable components as well as fixed components. Let's look at our first example. Suppose a firm manufactures MP3 players and sells them for $50 each. The costs incurred for the production and sale of the MP3 players are $200,000 plus $10 for each player produced and sold. We want to write a profit function for the production and sale of X players. So before we can do this, we're going to have to write a revenue function as well as a cost function. We'll begin our revenue function with the notation R of X, and we know that this is equal to a price per unit times a number of units. In this case, the number of units that we would be looking at is just X. We're producing and selling X players. So it's going to be some number times X, and then we see that we are selling these for $50 each, so this should be 50 times X, and a common way to write that would just be 50X. For the cost function, C of x, we know that there's a variable part as well as a fixed part. So the variable part, you can think about it in a similar manner to the revenue. You have some kind of cost per unit, so something is going to be multiplied to x, and then x is the number of units again. So when you examine the cost, there's a $10 cost per unit, and that's our variable component here. So this is the variable. And then we are going to add on the amount of the fixed cost, so for this example, $200,000. To just simplify my notation a little bit, I would call this 10x plus 200,000. Now, to create our profit function, we can just write P of x is equal to R of x minus C of x, and doing a simple substitution, we should see that that's 50x minus 10x plus 200,000. A little bit of algebra here at the end. You'll notice that 50x and 10x are like terms, so we can do 50x minus 10x. That's going to give us 40x. And then when you subtract 200,000, you should end up with negative 200,000. So p of x is equal to this function right here. Let's look at these three functions a little bit more. We have the revenue function graphed on the left, cost in the middle, profit is on the right. And first of all, let's look at the revenue function. You'll notice it goes through the origin 0, 0. The kind of common sense understanding of that is if you have 0 units produced and sold, then your revenue, the money coming in, would of course be 0. Cost does not go through the origin. It actually has a positive y-intercept, and the reason here being that if you produce 0 units, you still have all of those fixed costs that are associated with this business. So we expect that the cost function usually has a positive y-intercept. When you subtract the two functions to get your profit function, we see that it starts out negative because if we're not making and producing very much in the current situation, then we're going to have a loss for the company. But at some point, we hit a critical, we will call it a break-even point, and that corresponds to the x-intercept of our graph. Beyond this point, the company is profitable. So if our market research would lead us to believe that we could produce and sell more than whatever this value is here, it looks to me based on the graph it's about 5,000. If our research would lead us to believe we can produce and sell more than that, the fact that our graph is now in the positive region would indicate the company is profitable. If, though, we are only going to produce and sell some number that's lower than whatever this threshold is, the company is not going to be profitable. So in the context of this problem, we might be interested in knowing what the marginal is for any of these functions. So we could ask for the marginal profit, which is noted like this, or we could ask for a marginal cost, which is that MC with the bar over it, or marginal revenue. Now, what is a marginal? It's a rate of change with respect to the number of units produced and sold. So rate of change is kind of like the big thing that we focus on here. For each of these three functions, if I asked what is the rate of change of the function, we note that because each of them is just a straight line, the rate of change is constant the entire time. It ends up being just the slope of the line. So we can look at our revenue function. Our marginal revenue would be 50. We could put that in. Marginal revenue is 50. The marginal cost would be 10, and then the marginal profit would be 40. One good way to think about what is a marginal is it's the dollar amount that would be associated with increasing production and sales by 1 unit. So for any of these functions, I'm going to pick on profit here. If you imagine x is equal to some number, let's say 20, we could figure out what the profit is. If you increase x by 1, so let's increase it to 21, then the increase in your profit is going to end up being 40. Now, in these examples, coming up with the marginal was really easy because all of the equations are straight lines, but in future examples that will not always be the case. A lot of times the real world situation, your production, cost, revenue, these are not linear functions, but they might be functions that have some kind of curve to them. We're still interested in those situations in knowing what the marginal is, but we'll have to have a more sophisticated approach. We're going to have a calculus approach. Before we get into the next example, I'm going to review a couple of concepts from algebra. So the slope of a line, which is denoted m, is equal to y2 minus y1 over x2 minus x1. And this is anytime you are given 2 points, x1, comma, y1, and x2, comma, y2. The slope-intercept form of a line is a very popular way to write lines, would be y is equal to mx plus b. Here m is the slope and b is the y-intercept. And the point-slope form of a line, which I kind of prefer in these examples, is going to be y minus y1 equals m times x minus x1. Again, m is the slope. Here, x1 and y1 just reference the given point. So if you want to create a line, the generic strategy is From the given information, we need to find the slope. So sometimes we have to use this formula to do so. Once you have the slope, you can plug the slope into the formula, either of these two formulas. And then finally, you can find out what the y-intercept is if you actually need that. If the question ends up just asking us for an equation, but doesn't require that it be in the slope-intercept form, then really we can bypass step 3 and we can just plug the information that was given into this final form. So let's look at the example. We have a company charting its profits, and it notices that the relationship between the number of units sold and the profit is linear. And then they give us some information about how many units results in profit in 2 different situations. Now we can internalize these as like an x value and a y value. If the input of this function was 150, the output is 600. And if the input of the function is 200, then the profit is 3,300. So we want to come up with a line that would go through these 2 points. Well, we have a strategy listed above. First, we need to find the slope of this line. So m is equal to y2 minus y1 over x2 minus x1. When we subtract this, we should get 2,700 divided by 50, and then when we divide those two, I end up getting 54. This is the slope of the line, which also happens to be the marginal, in this case, the marginal profit. To come up with the equation of our line, I'm going to use that slope-intercept form that's listed first. Y is equal to mx plus b. The reason I'm picking on this is because they do want a profit function. So y, eventually, I'm just going to replace y with p of x. So my final answer here is going to be p of x is equal to something. Now, at this point, we're basically at step 2. We need to plug the slope into the formula. So y would be equal to 54x plus b. And the only thing we don't know yet is we don't know what b is. So off to the side, I'll go back to the left here. Let's copy that down. Y equals 54x plus b. And what we need to do is we need to plug these values in. So I have 2 points. I'm going to look at the first point. It has a y value, so the y value there was 600. It also has an x value. The x value there was 150. And we plug both of those into the equation. So 600 is equal to 54 times 150 plus b, and now we need to solve for b. When I multiply 54 times 150, I end up getting 8,100. And then to solve for b, finally, we would just subtract 8,100 from both sides of the equation. So 600 minus 8,100 ends up being negative 7,500. So that's our b value. It is negative, so when we write our final answer over here, p of x is equal to 54x minus 7,500. We will frequently be interested in knowing what that break-even point is for a profit function. So in a given situation, if you want to find a break-even point, there's kind of 2 approaches that you might want to take. So one approach would be if you start with the total revenue equation and the total cost equation, we can set these 2 things equal to each other and then solve. This would give us the x value for that break-even point. Alternatively, if you're given the profit function, or if you've already had to compute the profit function, you can find the zeros of that profit function, which correspond to those x-intercepts, and then that would give you the x value of the break-even point. So let's apply that strategy for the example below. We have a manufacturer selling a product for $10 per unit. The variable costs are $2.50 per unit, and the total cost of 100 units is $14.50. We want to give a function for total revenue, total cost, and profit. Then we're going to determine how many units the manufacturer needs to produce each day in order to break even. All right, let me give myself a little bit of space, and then we will start solving this. So we're going to begin with a revenue function, r of x, and we've said before that the revenue function is always a price per unit that you're selling at, so we're selling at $10 per unit, times a number of units, in this case just times x. Similarly, we can come up with a cost function, and the cost function is not going to be super easy to just immediately come up with. We know what the variable costs are, so it's going to be 250 x plus some number, which is the fixed cost, but they don't actually tell us what the fixed cost is, right? They haven't said the fixed cost is $14.50. They're giving us a total cost when 100 units are produced. So right now it's just plus b, but we're going to figure out what that b value is. And we're going to do so by using the information provided. 100 units is 1450. From that, we can gather that 100, if 100 is our x value, 1450 would be the y value. Okay, so let's apply that into the cost function. My total cost would be 1450. That's equal to 2.50 times x. We know what the x value is. That's 100 plus some fixed component. So after we've plugged these values in, we know everything except for b. We can just solve this equation for b. Let's go ahead and do so. 100 times 2.5 would be equal to 250 plus b. What that number 250 represents is it represents the variable part of our costs. So if we produce 100 units, that's going to add on $250 of expense. So then we just need to figure out what the rest of the cost is, what the fixed part is, so that in total, the variable part plus that adds up to be $14.50. Now, algebraically, you don't have to think about that. You can just subtract 250 from both sides. You're going to end up getting b is equal to 1200. But I wanted to point out that even this like number we compute along the way does have a meaning in the context of the problem. All right, c of x is equal to 2.50x plus 1200. All right, like we've done before, to compute a profit function, p of x, we know that profit is equal to r of x minus c of x. When we subtract these, what we're going to get, 10 minus 2.5 sounds like 7.5 to me. You can write 7.50, but it's not necessary. And then that negative sign will get distributed into parentheses, and it will be minus 1200. So p of x is equal to 7.5x. We've answered the first three questions that they gave us because we wanted to find a function for each of those three situations. Now we need to determine how many units the manufacturer needs to produce in order to break even. So I'll do this off to the side. We have a break even point. So to find the break even point, you can either set r of x equal to c of x and solve. That will give you the x value. Or you can set the profit function equal to 0, and that's going to be my method. So I'm going to put 0 in for profit. This is equal to 7.5x minus 1200. And the idea here is that if your company is breaking even, you have $0 of profit. So to solve this, we add 1200 to both sides of the equation, then divide both sides of the equation by 7.5. Let me pull out a calculator. I see that x would be equal to 160 units. So at this point, we need to remind ourselves what the question was asking. It asks us to determine how many units the manufacturer needs to produce in order to break even, and x was representing the number of units. So we have it. This is our answer. No further work is required. If, though, the question asks what cost is associated with breaking even, or how much revenue must the company produce in order to break even, then you would take this x value and you would plug it into the revenue function if they ask about revenue, into the cost function if they're asking about cost, and because it is a break-even point, we know that those two values would be the same. So if you plug 160 into R or into C, you have the same value for revenue and cost right there. Of course, if you plug it into profit, the profit is going to be 0 because it is a break-even point. All right, let's look at the situation from a slightly different point of view. So we've just examined all of the equations that are involved, but what would we do if we were given a graph instead? Now this is all of the same information as what was up above, but it's still worth thinking about how does this information relate to a graph? So here what we see is we have graphed the revenue function. This is the diagonal line R, and we've also graphed the cost function, and it's this other diagonal line C. So if we had graphed both of those, there's a number of questions that we could ask. First of all, we could just ask, what is the break-even point? And it's the place where the two functions are the same, and we would see, hey, 160 units would be required to break even, and that gives us basically the answer to the second question listed over on the right. What is the break-even point? In this case, the break-even point is 160, 1600. Keep in mind this y value corresponds to the revenue and the cost. It does not correspond to the profit. Let's back up. How do we determine the fixed cost from a graph? Now, we could do this even if they had not given me a cost function. So if you don't know what this is, you can still answer this question because we can look at the cost line and the fixed part of it would always correspond to the y-intercept. So on this line, we see the y-intercept is 1,200. We would say the fixed portion of the cost is $1,200 in this case. Next question over on the right, how many units must be sold to break even? That's 160. It's the number of units. It's the x value of the break-even point. What does the number 1600 represent? 1600, of course, is it's the y value when R is equal to C. R is your revenue, C is your cost, so it's the revenue and the cost associated with breaking even. I'll write something similar to that. It's just the revenue and cost associated with breaking even. And one final question, how can we use the graph to estimate the marginal cost and the marginal revenue if the slopes weren't listed? So if you didn't actually have these, how would we know what the slope is? Well, we know that m is equal to y2 minus y1 over x2 minus x1. Let's do the revenue first. We know that the revenue function goes through the point 0, 0, and it also goes through the point 160, 1600, so we can now plug these values into the slope equation to come up with our marginal revenue. What about the cost? Cost has a y-intercept of 1200, so it goes through the point 0, 1200, and then it also goes through this break-even point, so that's 160, 1600, and we can now plug these values into the slope equation if we want the marginal cost. The last thing we talk about in this section is supply, demand, and market equilibrium. The law of demand states that the quantity demanded is going to increase as price decreases. The law of supply states that the quantity supplied will increase as the price of the product increases. The third definition states that market equilibrium will occur when the quantity that is demanded is equal to the quantity that is being supplied. And we see that happening here in this graph. We have a supply function which has a positive slope, demand function has a negative slope, and whenever these two things are equal to each other, we would call this the equilibrium point, and that's going to be composed of two different values, one of them being the equilibrium quantity, the other being the equilibrium price. When we actually go to solve problems that involve equilibrium prices and quantities, We typically don't graph these in this class. What we'll do is we'll just be given two equations. One of them represents demand, one of them represents supply. And from those two equations, we will be able to just do an algebraic analysis to determine what that equilibrium point is. So in this example, we want to find the equilibrium point for the following supply and demand functions. We are given the demand function. You might notice that it has a negative slope, so even though this is labeled as demand, you would have been able to determine that this was the demand function even if it had not been labeled. In order to find equilibrium, price, and quantity, we want to basically solve this system of equations. If you haven't done this in an algebra class recently, there's a number of ways to do so, but substitution is going to be the primary method that we use. Now, in this example, both of these things have already been solved for p, so that is a great place for us to start. I'm going to begin by writing the top equation down. P is equal to negative 5q plus 200. And then what I'm going to do is I'm going to take the second equation. It's already been solved for P, and I'm going to substitute it in for the P in the first equation. So what we have here then is on the left side, we get 13q plus 20 is equal to whatever we had on the right side previously. So that's negative 5q plus 200. So now that these two equations have been set equal to each other, we can go ahead and do a little bit of algebra. I'm going to start by adding 5q to both sides of my equation. That gives me 18q plus 20 is equal to 200. I'll subtract 20 from both sides of the equation. I want to get rid of the 20 on the left. Then that gives me 18q is equal to 180. Divide both sides by 18. And we end up seeing that q is equal to just 10. Now, this is a great time to go back and reread the directions. The directions said to find the equilibrium point for the following supply and demand functions. A point is going to be the p and the q values together. So just following the lead of the example that we see up above here, if q is on the horizontal axis, then p would be on the vertical axis. So then q takes the place of x, and p takes the place of y. So q is in place of x, p is in place of y. We've just found that q is equal to 10, so I'm going to call this 10 comma something, and we need to figure out what the p value is. Should be fairly simple to figure out what p is. We have two different equations that you're allowed to work with, and you already know what q is. So for the equilibrium point, q must be equal to 10. We can take this and substitute it either into the second one or the first one. I'll just pick on the second one because everything's positive there. So to finish this problem up, we have p is equal to 13 times the value we just computed plus 20. So then this would be equal to 130 plus 20, and then that would be equal to 150. We can put that value in, 150, for the price. Now, you will want to pay attention to the instructions in WebAssign. They may indicate that you should list your point as P first and then Q, but if they don't, then just kind of following the example that was in the book, we'll put Q first and then P. That finishes the notes. I will just mention that if anyone is interested, the textbook has an interesting explanation of how taxation would affect a market equilibrium. So if you're interested in that, you can find that in section 1.6. It should be the very last topic you see before the textbook goes into the exercises.